So I have this SMC ball screw actuator with a stepping motor and a brake on it. It's not a servo motor, it's a stepping motor. So I'm using a Copley TEL. This is a TEL 9010. This does 10 amps continuous, 10 amps peak, but there's another 5 amps continuous, 7 peak model. And I'm running on a 24 volt supply. Honestly, that's not enough voltage to go very fast with this. It's a stepping motor, so I'll explain that some more in a moment. But I've got the TEL with the stow bypass jumper. That's for the safety, and we sell the bypass jumper to make it easy, but you just plug it in and it bypasses the safety circuit to turn on the H bridge. It's disabled right now, but the fast blinking turned into slow blinking, so we just need to enable it. And I can enable it on the control panel. I'm in a stepper mode. I've disconnected my EtherCAT master from the system so that I can then enable it. Sometimes if you disconnect the EtherCAT master, you may have to reset the drive. That's fine, but in order to jog, you can't have the master connected. And you can see I've used in the Copley serial adapter. This is an RJ11 to USB on my computer. It's a model number SER-USB-RJ11, and it's a Revo 2 for Windows 11. So Windows 10 migrated to Windows 11, and Prolific migrated from an old chip to a new chip. The old chip is obsolete, so you got to get yourself this. I always use this, even when I have an EtherCAT master, so I can monitor what's going on in the system. So get yourself one of these, and if you just monitor, it's fine. If you want to jog it, you got to disconnect the EtherCAT master, literally unplug it here. You'll get a fault, a command input fault. You reset the drive, and then it comes up without the master having configured the state machine. Anyways, we're going to give this thing a little jog here, and I'm jogging in the negative, in the positive, and I was able to hit about 300 RPM. So here's top speed. That's like 5 revs a second. Let's do 240. So yeah, it's a stepper. It's a little bit of noise. Copley is usually like the quietest there is, but there's the ball screw and whatnot. So that's a 6 millimeter pitch. So 1, 2, 3, 4 revs per second. That's like an inch per second, 24 millimeters, maybe 30 millimeters per second. I'm kind of running out of top speed here on 24 volts, and I'll explain that in a moment. So we'll take a quick peek at CME here, and you can see in the basic setup, I got 2 instances of CME going here. Bear with me for a moment. Okay, so basic setup, change settings. It's a rotary motor. This one has a brake, so we got to say, yeah, there's a brake. Next, there's no feedback. I mean, they do, quote unquote, have some feedback at SMC, but it's serial port, RS-232. You got to wiggle the motor to then get the absolute position using Modbus, RTU. It's not a normal standard absolute feedback, so we can't use it. We have to develop something, but it's not normal to do serial port ASCII. Like, they have servo motors that have normal feedbacks on it. Maybe they're proprietary and we have to work together to get the feedback protocol specification, but Copley can adapt to many different normal things. And like in the list, you can see there's Tamagawa in here, Absolute A, that's very common. For applied materials, maybe there's a Mitsubishi, but they have a unique spec. Anyways, yeah, if you have a brake, you want to take some time to stop. You want to turn the brake on when you get some speed, and you want to give it some time for the mechanical click solenoid to engage so you can turn the brake on so you don't drop wafers. So that's the basic setup. And I'm in a disabled mode. You can't communicate with the EtherCAT master. I enable it. I can communicate it with the EtherCAT master. And then if I jog it, I can jog it. So I'm going to show where we put the data for the motor. So SMC, here's the model number. You know, this data is not readily available, so you have to like try to squeeze it out of them. I measured the resistance, and I think they provided me some data for the motor, so it's 10 millihenries. That's a lot of ohms, right? So if you're going at 1.8 Newton meters with 1.1 amps, like it's a spinning motor, so you got some back EMF. So 24 volts doesn't cut it. I'm going to show how to calculate the back EMF. So use the calculator, speed torque curve, and we said the amps was 1.1 and the Newton meters was 1.8. Let me double check that. Yeah, 1.8 Newton meters, and I got 24 volts, and I got 8 ohms. And it's a PWM amplifier, so you don't get 24 volts at the output. You get like 95% of it, or 23 volts. But the point is, you can see this, you cannot get 1 amp of current through 8 ohms plus some back EMF, right? So you can't go very fast with twice the current. You go a little faster with 1.1 amps, but at some point the back EMF rolls you off. And so you run out of torque. Okay, so you can't fight gravity and hold the load and accelerate the mass and overcome the friction. It's just a fact of stepping motors. Things get a little bit better with 48 volts, so you can go a little faster before you roll off. And then, of course, 80 volts, Copley can do 80, so you can go a little bit faster at full torque, or even, accelerating the mass torque. And so let's take a look at that. I've already done the current loop tuning here. So the bandwidth is about 1 kilohertz. You can test that, but I'm going to skip right to the scope here. So first we'll do like the current auto setup. So this is the commanded current and the actual current. And, when the gain's too high, I double it. You see the ring, gain's too high. So cut that in half. So double, double, double till you see ring, then cut it in half. And then the same thing for the integral windup. You double it. You see the integral windup, you're overshooting. That's too much integral gain for the current loop. Put that back. And so this is a nice, critically damped current loop response, about 1 kilohertz or 800 hertz or maybe less, because you don't really need to go that fast, and you're going through like 50 poles. So, so many cycles per second times 50. That's not a very high frequency, so you're probably fine. And then for doing the profile, auto setup checkbox, right? And you can see we're going to trace the profile velocity, the actual current, and the commander. This is open loop. There's no feedback, right? So if you had an incremental encoder on the motor shaft, then you could do encoder corrections. If you have an absolute encoder, the one on this motor is not what you want, right? It is, you got to move first before you get the position, and then you can move. It's not normal, okay? So don't use this unless there's something that's normal, and then we can use a normal drive with a normal stepping motor. Anyways, trajectory limits, I'm going to just start off at a nice 60 RPM, 1 rev a second, 6 millimeter move with some XL and some decel. And I got to double check so the feedback was supposed to be 4096 absolute. It's count, so I'm going to do 4096 counts for 1 rev. It's a 200 full step, but I can set my micro stepping to anything I want. I usually match the encoder. So a 4096 count for 1 rev encoder gets 4096 micro steps, and every count is 1 micro step. It's just logical and easy to do the math. You could have more count. You could have a 131,072 BIS-C absolute encoder, and that would work with this drive. and get a lot of count. So you can do a lot of micro steps. Anyways, I'm just going to do a real simple 4096. That'll be 1 rev. I'm going to go in the positive direction and 1 rev. And the current limit warning is normal because this is running at the boost and the run current. So I got the boost and the run set to the same, and then I got a hold current of 0.5 amps and then fold back. So this holds against gravity. Maybe you need more, maybe you need less. Motors get hot if you do the full rated current. So you need to have enough current to hold against gravity. I'm going to double the speed, and you'll start to see the current. At this moment, for this profile, the commanded and actual current are right on top of each other. So that's good. You're getting all the torque and force you need. Okay, so now I doubled the speed, and what happens when you go fast, right? The motor generates back EMF, so you get less voltage. And look what happens to the current. Now I'm down around like 1 amp, a little bit less. So the back EMF is causing the Ohm's law, which is true. Ohm's law is true. Voltage minus the current times the resistance. It's 8 ohms. Let's remember again, 8 ohms times 1 amp is 8 volts. So I don't have 24 volts anymore. I'm down minus 8 volts, plus the back EMF. Okay, and this will show us the back EMF. That's in radians per second. Oh, 171 volts per 1,000 RPM. There's no way 24 volts is going to be able to go that fast. And you can see what happens here. Now let me go too fast, 300 RPM. And so that was a short little 1 rev move. Maybe we'll do a 10 rev move. But look at how low the current is. It's like 0 amps, right? Somewhere around 0, you get no torque or no force, and you stall. Okay, so I'm going to go in the negative direction because I'm going to run out of room. So yeah, this is in danger of stalling. And again, it's just simple physics here. It's nothing fancy, nothing complicated. So I just look at the voltage bus, okay, and then the voltage terminal stepper and the voltage terminal. So here's the voltage stepper, and then there's another one, the voltage terminal servo. We got to look at both of those and add them up like vectors to make sure we have sufficient. And you can see, yeah, so this voltage is almost 24 volts, and this one is like 10 volts. So there's two, like you're running out of voltage, plain and simple, even with the max speeds. Here's the, circular limiting, hexagonal or square limiting. That gets you the full voltage. But yes, the spec says you can go this fast, but not really, and get the torque. Like, again, look at the speed torque curve, and it tells you how fast you can go with 80 volts. So here's 48 volts. Oh, heck, I got 24 volts, right? So I'm barely able to hit these speeds. Like the current's down to 0. Maybe I have a little bit more voltage or something. Yeah. So I'm getting lucky here. Running on this 24 volt supply, but even a 48 volt supply shouldn't be able to hit very fast. Anyways, it's a first approximation calculation. So, but the point is, you need your current. Okay, so you need to bump up the bus voltage, or use a servo drive. They have the same motor here. Like they have a servo motor, a 100-volt motor, a 200-volt motor, and we got a Zenus drive, Zenus EtherCAT, Zenus Compact EtherCAT. Does the brake, does the servo motor. It's a special servo motor. I don't know if it's a Tamagawa or a Mitsubishi, and there's some fancy feedback, but we should be able to drive it with this if they share the proprietary protocol. We can develop it for applied materials or semiconductor. That's no problem. Anybody else, I don't know. You got to have an NDA and make sure it's okay with SMC and whoever's feedback it is. So that's it. Thanks for your time.